we're looking at the chemistry behind a lead acid cell. So the main points you need to remember are that a lead acid cell has a lead anode, a lead oxide cathode, and a sulfuric acid electrolyte. So let's flesh out these first 2 points. So we have a lead anode. We know anodes always have the sites of oxidation. And the simplest way of summarising what's happening at the anode is that lead is being oxidised, so we're creating the Pb2 plus ion plus 2 electrons. Oxidation is always loss of electrons. We'll come back and represent that equation in another fashion in a moment. Moving on to the lead oxide cathode. We know that cathodes is always where we have reduction happening. So we've got lead. Now, we just need to look at the charge in lead oxide. So PbO2, this is our oxidation number work. So we know that whatever the oxidation number for lead is, when we add it on to 2 lots of the oxidation number for oxygen, overall the charge is 0 because lead oxide is a molecule. That gives us that the effective charge or the oxidation number for lead in lead oxide is +4. So I'm going to represent that in my simplest form of the equation that's happening at the cathode. So Pb4+, now reduction is gaining electrons. If I add those 2 electrons from my anode reaction to my lead 4+, I'm going to make Pb2+. And this is summarising the chemistry in the basic form of what's happening in a lead acid cell. And because the lead acid cell is reversible, I need to specify that we're looking at it operating in this case as a galvanic cell. Now we know that a galvanic cell is taking chemical energy, so and creating electrical energy. So it's being used in the car to actually start the car. Now as the car's running, the battery's actually recharging and it's working in the reverse, but we're looking at it just starting the car operating as a galvanic cell. Now unfortunately we need to make these 2 equations into another form that's a little more complicated. And to help us get there, what we need to do is, wherever we've got lead 2+ written, we need to represent it in our expanded form as lead sulfate. And wherever we've got Pb4+ represented, we represent it as lead oxide. And that one's simple because that's how we arrived at the 4+ anyway. So let me do that step first, leaving that as it is. Now, we're putting that as the sulfate, and still got the 2 electrons. I'll fix up the second one while I'm here. We're representing that as lead oxide, plus 2 electrons goes to lead sulfate. Now at this stage it should be screaming at you because conservation of mass, for example in the first equation, you can't suddenly have created sulfur and oxygens. But we can balance that by putting just the sulfate ion over there, because we know that that is there in solution because our electrolyte is sulfuric acid. And that's the expanded form of what's happening at the anode when a lead acid cell is operating as a galvanic cell. Now we're not quite there with our reaction at our cathode yet for similar reasons. For example, we've got sulfur on this side, S and none here. So again, I would need to be placing the sulfate ion over here as a species that it's around that has the sulfur in it. Now, at this stage, we've got a problem with charges, if nothing else, because this side of the equation is 0 charge, and at the moment, this side of the equation is a -4 charge. So the only thing that we can introduce that's going to be carrying a positive charge to cancel out that would be the hydrogen ions from the sulfuric acid electrolyte. And we would need to be having 4 of those so that the charges are cancelled. Now, we're going to then have a problem with hydrogens being on this side and none on this side. And when we're always balancing redox reactions, we're always able to add water where we need to just to balance it because we're doing in an aqueous solution. And I think atoms-wise, we've needed 2 here to give us the 4 hydrogens on both sides. So that's the expanded form of what's happening chemically in a lead acid cell at the cathode. Thank you for watching.